Hello dear colleagues, today we will continue our series of seminars on the basics of radiochemistry. And today we will solve some tasks that are practical tasks and related to the use of radioanalytical traces and how we can solve some specific problems with use of the radiochemical methods. So, first task is related to the absorption of zirconium containing compound on the glass. In this case, it is just a vessel where the solution of the diluted solution of zirconium is located. So we have 50 milliliters of the solution containing 8 to 10 to minus 7 mole of zirconium hydroxide that is labeled with zirconium 95. And the activity of this zirconium 95 is 12.5 gigabecquerels. And we know the surface area of the glass of this vessel that is equal to 25 squared centimeter. And we know that one ion of the zirconium occupies the surface area equal to 2.5 to 10 to minus 15 squared centimeters. And the question is how the specific activity will change during the time due to the molecular adsorption and if we know the half-life of zirconium 95. So, to solve this task, of course, we will need to use the law of radioactive decay that can be written as activity is equal to lambda n. And we will see how the activity will change and what amount of zirconium will be absorbed. So first of all, we should calculate how many molecules of zirconium will be absorbed on this surface. So we know that the total surface area is equal to 25 squared centimeters, and we know that the surface area that is occupied by one ion is only 2.5 10 to minus 15 squared centimeters. So from this we can calculate the number of absorbed ions. So just a total area divided by this one ion, and it will be 25 divided by 10 to minus 15. So it will be simply 10 to 16 ions, and we will take this number into account. We know that the total concentration of zirconium is 8 10 to minus 7 mole in 50 milliliters, but we don't need the concentration. At the moment we just need to know this amount of the zirconium. So from this we can calculate how many ions we have in solution. So it is simply sorry, not this. It will be simply n, that is equal quantity or amount of the ions multiplied by Avogadro number. So it is our 8 to 10 to minus 7 moles multiplied by 602 to 10 to 23. So we know from these calculations, so it will be equal to 4.8 10 17 ions in solution. Or if we have this number that can be absorbed, we can rewrite it maybe more convenient for us, maybe not so correct, but we can write it like this. So this is the number in solution, and this is the number of ions that can be absorbed. Let's put some notation here that it is adsorbed atoms. And thus, we know that 10 to 16 ions will be absorbed, and that means that the final amount of ions will be our total amount minus this absorbed amount. That will give us 10 to 17 ions. What we can do further, we can calculate, for example, the amount of the zirconium, the activity of zirconium that is absorbed on these walls. Of course, it will be the same fraction. So let's call it fraction. It will be 1/48 of the initial activity, because 10 to 16 is absorbed, and initially it was 48 to 10 to 16 ions, and thus we can calculate the amount of adsorbed ions. We know that the initial activity is 12.5 gigabecquerels. We divided it, and we get something like 0.26 gigabecquerel of the activity is adsorbed to our glass. Now about the specific activity that is now still in the solution. Again, we can use this fraction in solution. It will be the rest divided by the initial amount, and of course we just multiplied it by the initial activity, and it will be 12.24, let's say, gigabecquerel in solution. And what we know else, the volume is 50 milliliters. Here. And thus the specific activity that we can write as a small a will be our remaining solution, remaining activity divided by, let's say, 0.05 liter, 0.05, sorry, and it is gigabecquerel. And we will get something like 2 gigabecquerel per liter. Okay. And you can see that if the, let's try to make to solve another task. Assume that there is no stable zirconium. We know that this zirconium hydroxide is only labeled with our zirconium. But now let's assume that there is no stable zirconium and only radioactive zirconium in solution. we will see how it will change our result. So from this result, when there is a lot of stable zirconium in the system, we see that only a small fraction of the zirconium is adsorbed on the glass. But we will see how it will change if there is no stable zirconium in solution. So now we have only radioactive zirconium, zirconium 95 in our system, and the half-life, I will just go back, is 64 days, and the activity is 12.5 gigabecquerel. And the same surface area, 25 square centimeter, the same specific area for one ion. Okay, and what we will do next? We will calculate from this equation the total amount of zirconium 95 in the system. So we will do it like this. Multiplied by yeah. So we know the activity 12.20. Giga means 10 to 9 becquerel. We know the logarithm 2, and we multiplied it by the half-life, 64 days. But as far as our activity is given in becquerels, we have to convert days in seconds. So we multiply days by the number of hours and by the number of seconds in 1 hour. And thus 10 to 17 ions, let's say. Okay. And from the previous task, we remember that the number of adsorbed ions is equal to 10 to 16 ions. So you can see that in this case, it is already 1/10 or 10% of all ions will be absorbed. And we can easily say that the total activity will also decrease to 10%. And so the final activity in solution will be 12.5 multiplied by 90%. So it will give us gigabecquerel in solution, and thus the specific activity 2 to 5 gigabecquerel per liter. So we took again the volume of 50 milliliters. Okay, you see that the addition of stable zirconium ions decrease significantly the adsorption of zirconium ions on the walls of the glass vessel or onto another mineral surfaces or some other surfaces that can exist in the system. Okay, we will move to the next task. So the next task. So the researcher has a setup, means some detection system that can measure reliably the count rate equal to 10 counts per minute, or CPM. And the registration coefficient phi is equal to 0.1. So what is the detection limit of element M, some element that is not really important for us what is the specific element. And we measure the concentration of or amount of this element by the registration of the radiation that is coming from its isotope with the mass 100, and the content of this isotope in natural mixture is equal to 10%, and decay constant is equal to 10 to minus 18 reversed means. So what is the detection limit in this case? Let's assume that we need to determine the minimum mass mean that we can measure with this detection system. What we know? We know the count rate, E, that is equal to 10 CPM. And we know the registration coefficient phi, 0.1. And we assume that this count rate, 10 CPM, it is already with subtraction of the background count rate. Thus, we can easily, we remember that the count rate is related to activity with this coefficient. Thus, we can calculate the activity that we can measure with this setup. So the minimum activity will be equal to 10 CPM divided by the registration coefficient 0.1. So it will be simply 100 disintegration per minute. So it is dPm. Now about the mass of this isotope. From this we can calculate the number of atoms and minimum that we easily calculate from activity minimum divided by decay constant. So, and we take our numbers, it is 100 dPm divided by 10 to minus 18 minute and minus 1. So it will be 10 to 20 atoms, let's say, of this isotope. Then we know that this isotope with the mass 100 is only 10% of the total content of the naturally occurring element M. And thus the end total minimum will be 10 times larger than the minimum amount of the isotope 100. So it will be 10 to 21 atoms. So it is atoms of the specific isotope, and this is atoms of the whole element M. So from this we can calculate the minimum mass as number of these atoms divided by Avogadro number, and with multiplication of the atomic mass, and let's assume that the average mass is equal also to 100, or very close to 100. So it will be 1/6 or around 0.7. In this case it is grams. So that means that even with such a not very high efficient detection system, we can easily measure like milligrams or hundreds of milligrams of this material just by the detection of the radiation that comes from the naturally occurring radionuclide. Okay, we now finish with this task, and we will go to the next one. Okay, now the next task. Now the researcher has more or less the same setup, and this registration system can measure the activities with or count rates equal to 54 counts per minute, and the registration coefficient is 0.05, and it is our task to determine what the specific activity should be for this sodium chloride in order to detect this certain mass of sodium chloride with use of this system. It is just an example of the task that we usually solve during our research activity, because if you know the parameters of our system, of our counter, and we are assuming that the lowest concentration in our system will be 10 to minus something, either mole per liter or grams per liter, and we need to add some tracer in the system, and we need to understand what amount of the tracer we should add to the system to detect it, even if the concentration will be at the very low limits, very low level. And this is an example how we can solve these tasks. So we know again that the count rate, the minimum count rate, is equal to 54 counts per minute. And we can directly recalculate the activity that we can measure. So it will be 54 divided by 0.05. So it will be 1080 disintegration per minute. This is the activity that we can measure, the minimum activity that we can measure with this setup. And we need to detect this minimum mass that is equal to 2.7 gram. And thus we can calculate directly the specific activity as activity divided by this mass. It will be 1080 divided by 10 to minus 10 to minus 7 gram. But also we have to convert activity from dpm, disintegration per minute, to becquerels, because we need to calculate becquerels per gram. So we recalculate it like this, and 9 to 10 to 7 becquerel per gram. So this is our final activity, but let's solve another additional task. What the amount of the sodium 22 isotope will be in this system. So we now know the specific activity, and by knowing the half-life of this isotope, we can calculate this amount using half-life. So it will be activity divided by. So, and let's calculate it. So it will be, let's take 1 gram of this labeled compound. And again, we have to convert years to seconds with this simple calculation. Oops, sorry. So finally, we'll get 106 to 10 to 16 atoms, and thus the mass of this isotope will be 10.6 10 to 16 atoms divided by Avogadro number and multiplied by 22, thus the atomic number, and it will be only 3.9 to 10 to minus 7 gram. So even if we add such a large activity to our system, it will be only a small addition of the mass of this isotope, of this radioactive tracer in our system, so it will not affect on the mass balance, for example, for the whole system. Okay, let's go to the next task. Here is an example how we can use the radionuclide tracer to determine the unknown volume of different liquids, like blood, for example, in the organism, or it can be the volume of the lake or some other parameters that we cannot measure directly. And with use of the so-called isotopic dilution, we can estimate the amount of this unknown parameter. So let's go to the task. We need to determine the blood volume in the animal with injection of just a half milliliter of tritium labeled water. We know the specific activity of this tritium water, that is quite small for tritium, and then we take out only 0.2 milliliters of blood. And we measure this blood with liquid scintillation spectrometer with known detection coefficient, and determine that the count rate is equal to 100 CPM. And thus we should calculate the blood volume of the animal. So what we know from this task? First of all, we can easily calculate the total activity that we added to the animal. So it will be this activity, the activity will be equal to our specific activity multiplied by the volume of the added activity. So it is 2000 becquerel per milliliter multiplied by 0.5 milliliter. So it will be simply 1000 becquerel. And then we should calculate the, so it will be the initial activity, let's say. And then we can calculate the activity of our blood sample. It will be count rate that we measured divided by detection coefficient. So it will be 100 counts per minute divided by 0.6. And as far as count per minute, so we have to convert it to the counts per second. So we have to divide it by 60. And we will 2.78 becquerels. So this is the activity of our 0.2 milliliters of blood. So we see how different the activity that we added initially in the system and the activity that we already measured. So the activity of our sample, so it is the relationship between this activity will be the relationship of the whole blood, let's say V0, to the volume of our blood sample. And thus, from this, we need to calculate this V0. Yeah. This V0 will be the volume of our blood sample multiplied by this ratio. And thus, the blood volume in animal will be equal to 0.2 milliliter multiplied by 1000 becquerels divided by 2.78, and thus we will get 72 milliliters. So it is some small animal, as we can see from this whole blood volume, but it is very illustrative example of how we can use this dilution without hurting animal, for example, or without measuring the whole volume of the some huge vessel. We can add the same amount of tritium labeled water in or some other traces like cesium, for example, or some shorter-lived traces to exclude the long-term contamination of the natural lakes or underground lakes. This method of radionuclide traces is widely used in different environmental researches. Okay, the next task. So the next our task is looking quite long and maybe looks quite difficult, but we will try to understand the whole task step by step. So we can use the radionuclide traces to solve different tasks, from the animal blood volume to some thermodynamic studies. Like in this task, we have to determine the solubility product of the strontium phosphate, or of course we can use the same technique to calculate the solubility product of any other compounds. What is the problem? That when we determine the solubility product of hardly dissolving precipitates or compounds, we have in solution a very low concentration of our components, and thus it is very often impossible to measure them by other techniques without using the radionuclide traces. And we will see how it works, at least in the case of this strontium phosphate. So let's see the conditions of our task. First, to obtain this strontium phosphate, the strontium chloride solution with this certain concentration of strontium chloride was used with content of some strontium 89, that is a radioactive nuclide, a radioactive isotope of strontium. Then, to determine the specific activity, part of this solution was diluted 50 times And the activity of this diluted solution was measured, and it was determined as 17,050 CPM per milliliter. Then some sodium orthophosphate was added to the solution of strontium chloride, and the precipitate was formed of strontium phosphate. And the volume of this strontium chloride solution was 100 milliliters, but honestly, it doesn't matter what is the volume of this solution. Then, what is important that after long stirring of this precipitate, in 50 milliliters of sodium perchlorate of a certain concentration, the activity, the specific activity of the saturated solution was 52 CPM per milliliter. So this resulting saturated solution over the strontium phosphate was only 52 CPM per milliliter. Thus, we have to determine first the solubility of strontium phosphate in units of mole per liter, and then to calculate the solubility product of this salt. And we will see that as far as we know, the concentration of background electrolyte of sodium perchlorate, we can calculate the thermodynamic activity coefficients, and it's already done. We know that the activity coefficients for cation means strontium is 0.87, and for anion, for phosphate, it is 0.73. So I will remove this text to have more space. So now what is the task? We have a precipitate of strontium phosphate, and in the solution it is always dynamic processes of dissolution and precipitation of this compound. And the solubility product is the product of this concentration of strontium and phosphate with the strontium 2 plus, with the degrees of their stoichiometric coefficients, like this and this, going to the respective degrees. Okay, but as far as solubility product is a thermodynamic parameter, we will multiply these concentrations by the activity coefficients of strontium and phosphate, and we will not forget the degrees, the same degrees. Okay. Now, what we need to calculate, it is the concentration of strontium and phosphate. From this equation, you can see that the concentration of phosphate anion is related to the concentration of strontium. And from this equation, so all the strontium ions and phosphate ions, they can go only from the strontium phosphate. Thus, if we know that the concentration of strontium phosphate is X, so it is strontium phosphate, so X mole per liter, let's say. Then the concentration of strontium cations will be 3X, because 3 strontium ions will come from one molecule of strontium phosphate. So it is strontium. And the same for phosphate, it will be 2x. And if we will take these numbers and we'll put them in solubility product, we will get this equation. Will be 3x 2x squared, then this coefficient for strontium, for phosphate, and thus it will be 27, 3 cubic, it will be 27 multiplied by 4, it will give us 108, x in degree 5, and then this thermodynamic coefficients. Okay. What we need to do is to determine now the solubility of strontium phosphate. And the saturation solution of the strontium phosphate, that means that if we have a precipitate of strontium phosphate in the system, and due to the slightly slight solubility of this precipitate, we have the strontium and phosphate ions in the solution over this precipitate, and as far as it is the dynamic process, the concentration of these ions of strontium and phosphate cannot be higher than the solubility product of this precipitate. So, how we can calculate the concentration of our strontium phosphate? We know that for this concentration of sodium of strontium chloride, 0.005 mole per liter of strontium chloride, the activity of the solution that was diluted 50 times is 17,050 CPM per milliliter, and it is diluted 50 times. Thus, we have to multiply it by 50 to know the real activity of the solution, and we will express it also as CPM per liter to have the same dimensions. So we will multiply it by 1000. So, and if we will calculate it, we will have 8.525 to 10 to 8 CPM per liter now. Okay. And now we can recalculate it to the specific activity of strontium. As far as we know the concentration of strontium, we know the activity of this solution. Thus, we can simply divide the specific volume activity of the solution by the concentration of the strontium chloride. So it will be 10 to 8 divided by 0.005. Thus, we will have 1.705 to 10 to 11 CPM per mole of this sample. What next? Now, as far as we know, the activity, specific activity of the saturated solution is, let's call it A2, that is equal to 52 CPM per per milliliter. And the whole activity of this saturated solution is coming from strontium. Thus, we can easily calculate the activity of the strontium in this saturated solution. Thus, it will be, so the C2 of strontium will be activity, specific activity of this solution divided by the activity of strontium, and it will be 52 CPM per milliliter. And again, if we would like to express it in liters, we have to multiply it to 1000 milliliters in liters, and divided by 1.705 to 10 to 11 CPM per mole. And now we will get exactly this number, 305, 10 to minus 7, and it is mole per liter. Okay. Now we know the concentration of strontium, and we should recalculate it to the solubility of strontium phosphate. And we see that the concentration, this X of strontium phosphate, so let's call it strontium phosphate, will be 3 times lower than the concentration of strontium. So it will be 305, 10 to minus 7 mole per liter. Divided by 3. So it will be roughly 1 to 10 to minus 7 mole per liter. Okay, and now we will put all this number to this equation. So it will be 108 multiplied by x, so it is 10 to minus 7 in 5 degree, and then it was the activity coefficients for cation 0.87 cubic, and for anion it was 0.73 squared, so it will be equal to 3.8 to 10 to minus 34. Okay, so this is again illustrative example of how we can use the radionuclide traces to determine such a low concentration of the substances in solution, and it is not even the lowest concentration that we can measure. For example, with the short-lived isotopes with the half-lives of days, let's say, we can determine the concentration down to 10 to minus 15 mole per liters. And this is all for today's seminar, and see you next time.